Good morning, students. Here's a quick review on the topics for exam 3. Now, these questions directly help you score higher on the exams, but memorization does not help. You really have to understand the concepts that I'm trying to teach you in these questions. So, first of all, momentum. We know that momentum is a vector quantity, and momentum is defined as the product of mass and velocity. So that's a vector, it's the product of mass and velocity, and the unit of momentum is kilogram meter per second. So that's about momentum. Now, since it's a vector, you got to consider the direction of the object. So here you have a 0.1 kilogram object moving at 10 meter per second. And we know that if it hits a wall and it bounces back, let's assume that it bounces back at the same velocity. And we're asked to find the change in momentum. So the change in momentum is final momentum minus the initial momentum. And the initial momentum is what? It's 1 kilogram meter per second because it's 0.1 times 10. 0.1 times 10 gives you 1. And the final momentum is negative 1 kilogram meter per second. Why negative? Because the velocity is in the opposite direction. So that's negative 10. That makes it negative 1. So the change in momentum, which is final, take away the initial, will give you negative 2 kilogram meter per second. Or in other words, it's 2 kilogram meter per second to the left. So always remember, when you deal with momentum, you have to consider the direction like for any other vector quantity. So let's think about a related question. If you have an object at a height, and you drop the object from that height, it's going to hit the floor and bounce back, but it doesn't bounce back to the height from which it was dropped. So that's the situation. So here in this question, you drop it from a height of 3 meters and it returns to a height of 2 meters. And you have to find the change in momentum. Just think about that. Well, how do you do that? You use the concept of energy. Because initially, at that height of 3 meters, it has potential energy given by mgh. And when you drop it, just before it hits the ground, all of that energy becomes kinetic. So we can say that the potential energy at 3 meters is exactly equal to the kinetic energy just before it hits the ground or the floor. Now, using that, you can find the velocity just before it hits the floor. And then, using the same idea, you can find the velocity with which it starts moving up by using the same idea that the kinetic energy there becomes the potential energy at 2 meters. So that's what you do. So once you get the initial velocity just before hitting the floor, you can find the initial momentum, and then with the velocity with which it begins to move up, you can find the final momentum. Remember that the final momentum is opposite, so remember to have the negative sign. And then you can find the change in momentum as we did for the other problem. I hope that makes sense. All right, the second idea that we have to look at is conservation of momentum. And conservation of momentum is always true. We know that there are 2 types of collisions, elastic and inelastic. In an elastic collision, momentum is conserved, of course, but in addition, kinetic energy is also conserved. In an inelastic collision, only momentum is conserved. Kinetic energy is not conserved. So here you have the mathematical representation of conservation of momentum. Total momentum before collision is equal to the total momentum after collision. And then you have to know the difference between elastic and inelastic collision. By the way, there's also another type of collision, not another type, actually it's a type of inelastic collision. It's called perfectly inelastic. That's when two objects stick together after collision. So just like if you take a putty ball and throw it to a wall and it gets stuck on the wall, that's a perfectly inelastic collision, meaning that maximum kinetic energy is lost. In fact, all of the kinetic energy is lost in that case. So we could work out a question based on that. You have a 3 kilogram object, another 2 kilogram object, and you can see the 3 kilogram object is moving to the right at 20 meter per second, and the 2 kilogram is moving to the left at 10 meter per second. And that is before collision. And then they collide. After collision, object A is moving in the opposite direction. So now it's moving to the left at 5 meter per second. And we have to find the velocity of object B after the collision. So how do we do this? Apply the conservation of momentum, which is m1v1 plus m2v2. See, I took it as negative 10 because it's moving in the opposite direction, is equal to the final momentum of object A plus mass of object B, which is 2 kilogram, times the unknown final velocity of object B. See that? The unknown final velocity of object B, and then do the math. When you do the math, the first term is going to be 60, the second term is 20, you can see that, negative 20 actually. This is negative 15, and then you have 2 times VB. 60 minus 20, that's 40, and then you bring this over, it becomes plus 15, so that's how you get 55. So 55 is 2 times VB, and therefore V sub B is 55 divided by 2, which is 27.5 meter per second. So that's a simple application of conservation of momentum. But through this example, I want to show you that kinetic energy has been not conserved. Or in other words, the final kinetic energy is less than the initial kinetic energy. So we calculate the initial kinetic energy of the first object. Kinetic energy is 1/2 times mass times velocity squared. So you got 1/2 times 3 times 20 squared plus 1/2 times 2 times... See, I didn't put negative 10 there because it's not going to make a difference. You put a negative and square it, it's going to become positive. So you do that, you get the total initial kinetic energy as 700 joules. And then likewise, we find the total final kinetic energy. And when you do that, we're going to get a number that is definitely smaller than the initial kinetic energy. So 1/2 times 2 times, we got that as 27.5, so square that. And now we get, so when we do the calculations, you get 60 minus 20, and it's plus 15 here. So when you put plus 15, that makes it 25 on this side, and the velocity is 12.5 meter per second. And using that, you get, you know how I found that? Because when I put in the wrong number, I got a higher kinetic energy, and I knew that that can't be the case. So now you see that the final kinetic energy is less than the initial kinetic energy. So that's an inelastic collision. So in this problem, I had to move this direction of object A, and because I'm just making up the problem, right? I had to make it move to the right, because if it had moved to the left, then the final kinetic energy would be higher than the initial kinetic energy. So that's why I had to change that, and that changed the value of the velocity. I hope you get it. And then we move to the next one. This is also based on momentum. So here you have a car heading north, collides at an intersection with a truck of the same mass as the car heading east. So one is going north, you see, and the other is going east, and they collide there at the intersection. They have the same mass, and if they lock together and travel at 28 meters per second at 48 degrees north of east. So from the east, you've got to take an angle 46 degrees to the north. So that is north of east. Just after the collision, then how fast was the car initially traveling? Assume that any other unbalanced forces are negligible. Okay, so we need a diagram for this. That is the car moving north, that's north, that is moving east, and after collision they are locked together and they're moving that way. Okay, so that is the initial direction of one of the cars, and that angle is 46 degrees. So whenever we have this kind of a problem, we got to resolve the vector into its components, and that's why I'm getting 2m 28 cosine 46. Why is it 2m? Because both have the same mass. So m plus m is 2m, and so that, and this is 46, so this component is 2m times velocity, given us 28 cosine 46. So that is the x component of the momentum of both of the cars. Likewise, we have the y component of the momentum, which would be 2m times 28 sine 46. And once we get that, by the conservation of momentum, we know that this final momentum must be equal to the initial momentum along the y. Same thing with the x. These two must be equal. That is why I put m times v is equal to this. And also m times v is equal to this. But to solve it, we do the first one where I put the y components equal, and from that, I don't even need the x components. Just from that, I can get the velocity, which is 40.28 meter per second. All right, so now into rotational motion. There are many formulas in rotational motion, and this application where you have something rolling down an inclined plane kind of brings everything together. So I want to discuss that. So you have a ramp, an inclined plane, and you have an object rolling down. I know we did this in class, and we're trying to find the acceleration of this object as it rolls down. Getting to know how we get the formula is important, but I'll go fast because what's more important is understanding the final formula for acceleration. So this is a free body diagram coming up. You see the weight of the object acting down, and you have this component along the slope and the other component perpendicular to it, and then you have the normal reaction which is equal to this, and this is friction. Friction acts tangentially between the surfaces in contact, and it's opposite to the motion. And actually it's friction that causes a torque. Remember that this is a rolling object, which means it has rotation, sure. If there was no friction, it would not rotate, it would just slide down. So there is friction. So this is mg sine theta. By now you know that, and that is mg cosine theta. So this is the normal reaction, and that's friction. So considering the torque, the torque, what is torque? Torque is the product of force and their perpendicular distance. So if you look at this force F, and you know that this radius is perpendicular to that force of friction, so that's why torque is F times R. But torque is also I times alpha, where I is rotational inertia and alpha is the angular acceleration. But this is the relation between linear acceleration and angular acceleration. So we use that, to substitute. And so we get alpha is A by R, and we can use that here in place of alpha to make the formula F times R is equal to I times A by R. And then actually we can bring this R over to this denominator and then call it equation 1. So next up we look at the net force. The net force on this object. So the idea is first we looked at the net torque. Now we're looking at the net force. The net force is mg sine theta minus friction, because friction is opposite. And according to Newton's law, the net force must be equal to mass times acceleration. So that's what you see there. And then now I'm going to substitute for friction from here. It's IA by R squared when you have CdR there. And that's equal to M times A. Remember, we're trying to get a formula for A, so I have to separate A. And that's what I'm doing there. I brought this term over to the other side, that's why I changed sign. And then take out A. Once you pull out A, and you can now divide both sides by this quantity. So you have this formula coming up, mg sine theta divided by m plus I by R squared in parentheses. So that's what you have. So this gives the formula for acceleration of any object that is rolling down an inclined plane. But now assuming that this object is a solid cylinder. If it's a solid cylinder, now we got to substitute for I. And I for a solid cylinder, which is a disk actually, is mr squared by 2. So when you substitute that into this formula, you're going to get A is equal to mg sine theta by m plus. So in place of I, we put mr squared by 2 and then simplify that. So now the masses are going to cancel out and you're going to end up with, let me speed this up, you're going to end up with, I'm taking the mass out there, and you end up with 2 by 3 g sine theta. So this is an important formula that you got to remember. And it can be applied to different shapes. And I showed you what happens when you apply it to a disk. So now, if it's a solid sphere, what's going to happen? If it's a solid sphere, then we need to substitute the formula for rotational inertia of a solid sphere, which is 2 by 5 mr squared. When you do that, you get A is equal to mg sine theta by m plus 2 by 5 mr squared by R squared. See, the R squareds get cancelled, and you end up with, again, you have to pull the mass out, and that is 1 plus 2 by 5. That's why it became 7 by 5, okay? 1 plus 2 by 5. And then assume that the angle of the incline is 10 degrees. Then you can find out the acceleration. That's what I did there. I just assumed theta is 10 degrees. And so the acceleration of a solid sphere rolling down the ramp is 1.21 meter per second squared. Very important thing. Does it depend on the radius of the solid sphere? No, absolutely not. Why? Because it got cancelled. Does it depend on the mass of the solid sphere? No. So remember that. That could be a conceptual question that comes up. So next, let us look at elasticity. So you look at the definitions of the stress, strain, and Young's modulus. Excuse me. Young's modulus is linear stress by linear strain. Linear stress is F by A, and linear strain is change in length by original length. Now, the formula changes on this side because when you change a division into multiplication, you flip that. That's why it's length by change in length. So let's work out a question involving Young's modulus. So this question says a 0.600 millimeter diameter wire stretches 0.500% of its length when it is stretched with a tension of 20 newtons. What is the Young's modulus of this wire? The elongation or the stretching is given as a percentage. And that means it's that much over 100. So when it says it stretches 0.5%, then you know delta L by L is 0.5 by 100. But there are some dangers hidden here. Diameter is given. You've got to take half of that to get the radius. And again, it's in millimeters, you got to change it into meters. So you see everything that I've done there. This is how much so the ratio is, or the linear strain is. Area of cross section, because the cross section is circular, it's pi r squared. 0.3 times 10 to the negative 3 whole squared. And so I got the area of cross section. And once you get the area of cross section, simply substitute it into this formula. Force is given. That's the area of cross section. And you have the length by the change in length. And you get this as the Young's modulus. Young's modulus is going to be really high. Like, for example, the Young's modulus of steel is 2.1 times 10 to the 11. So when you get the answer that it is kind of, correct. The order magnitude is correct. All right, next what we have is a general discussion of torque. I already told you that torque is force multiplied by the perpendicular distance. But it's better to take it as the cross product of R and F, which obviously becomes RF sine theta, because the cross product of two vectors is the product of their magnitudes times the sine of the angle between the vectors, see? And when theta becomes 90, sine 90 is 1, so that's when the torque becomes maximum. So whenever you're looking for maximum torque, the force has to be applied perpendicular to whatever you're trying to rotate. Like if this is a door, you want to open the door. The most efficient method is to apply the force at right angles to the door. Not like this, but at right angles to the door. So you get maximum torque. And you need to know how to take the cross product, okay? So here is a question. A 95 Newton force exerted at the end of a 0.50 meter long torque wrench gives rise to a torque of 15 Newton meter. What is the angle, assumed to be less than 90 degrees, between the wrench handle and the direction of the applied force? So we're looking for the angle. Is the force given? Yes, 95. Is the distance given? Yes, 0.50 meter. The torque is also given. So that's a straightforward question, isn't it? That is the kind of diagram that you get. You're applying this force at an angle less than 90. The distance is 0.5. So this is where it's turning. That's the axis of rotation. So it's a simple application of the torque formula, from which you make sine theta the subject and then substitute the values. 15 Newton meter divided by the radius times the force. And when you do the calculations, you get that. Take the inverse of that and you get the angle. Can't have anything easier than this. a direct application. So considering significant figures, it's 18 degrees. Moving on, in rotational kinematics, you have several important formulas that compare with the kinematic formulas in linear motion. So I've listed the three important ones here. And this one simply is acceleration is change in angular velocity by time. This one, I call it the king, gives you theta. And by the way, theta has got to be in radians, not in degrees. It's got to be in radians. And remember that pi radians is 180 degrees if you ever want to change. So these are going to be very important, and let's work out a problem using some of this. So the angular velocity of a rotating rigid body increases from 500 to 1500 revolutions per minute in 120 seconds. That's revolutions per minute. We don't do anything in minutes. You got to change it into seconds. And the question is, what is the angular acceleration? What's that? That's alpha. And B, through what angle does it turn? So that's theta. So first we got to find alpha and then theta. Let's take it one step at a time. I already told you that what's given as 500 revolutions per minute needs to be divided by 60. So we get the revolutions per second. And what is that quantity then? That is frequency. Once you get frequency, you can find the angular velocity, omega. Omega is 2 pi times the frequency. So that's the track that we're going to use. So frequency, initial frequency is 500 by 60. That gives 8.33 RPS, rotations per second, and the final frequency is going to be 3 times that, which is 25 rotations per second. So once you get those, you can find the angular velocities. Here is the initial one, and that gives you 2 pi times 8.33. Now you're going to get it in radians per second. Likewise, the final angular velocity, again in radians per second, is coming up. So that's 2 pi times 25 radians per second. You need not calculate it right there. You can do it either now or later on. But the formula that we use to find alpha is this omega f minus omega I by delta t. Substitute the values, and when you substitute, I've taken out 2 pi to make the calculations easier. Divided by 12.0, that's how many that's 120 seconds, sorry, that's 120 seconds. And so you get alpha as 0.87 radians per second squared. Take care of the units. Next, you've got to find theta. Theta is found out using this form. Theta is equal to omega it plus 1/2 alpha t squared. And then that is 8.33 times 2 pi, that's omega I. T is 120. And then you plug in the values of alpha and t, and you get the result as 12545.5 radians. Here is a question from static equilibrium. Static equilibrium, where you have two conditions for static equilibrium. What are those? Number one, the net force must be 0, and the net torque must also be 0. Those are the two conditions. Look at this problem. It's a triangular plate in a horizontal plane, and 3 forces, F1, F2, and F3 act on the plate, which is pivoted about a vertical axis through point O. So the plate is on the table, and this is the axis, so it can rotate in that horizontal plane. And in the figure, F2 is perpendicular to OB. You can see that F2 is perpendicular to OB. Consider the counterclockwise sense as positive, which is usually the case. Counterclockwise is taken as positive in physics. And the sum of the torques about the vertical axis through point O acting on the plate, that is what we got to find. You got to find the sum of the torques due to the forces F1, F2, and F3 about the point O. Now, how do you calculate torque again? You take the force and multiply it with the perpendicular distance. That is what is being illustrated here through this problem. So first of all, this is 6.0 cosine 30. How do I know? Because this is 6.0 newtons. So this is 6.0 cosine 30. Why did I have to take the x component? Because we'll try to calculate the torque here. And so if this is the line of action of the force, OA becomes the perpendicular distance. You see that? OA is the perpendicular distance. So now to get the torque due to this force, you just got to multiply 6.0 cosine 30 times 0.6 meter. And is that clockwise or counterclockwise? If you know how a clock runs, then you know that's clockwise. This is trying to turn it clockwise. And next up, we will find the torque due to F2. F2 is already stated to be perpendicular to OB. So all we got to do is multiply that force with that distance. But that's going to be counterclockwise. You can see it's trying to turn it the other way. And then you got to find out the torque due to the third one. We'll come to that. So the clockwise torque, as I explained, is 6.0 cosine 30 times 0.6. Okay? So when you multiply that, you get the clockwise torque due to this, which is 5.70 Newton meter. Now the counterclockwise torque, I already explained that. That is F2 times this, which is, what is F2? F2 is 9 newtons, so that's 9 times 0.80, which gives 7.2 Newton meter. And wait a minute, why haven't we even considered force 3, F3? Because F3 is acting right at the point O. That means there is no distance between them, which means the torque is 0. So if a force is acting exactly at the pivot or at the axis, then it creates no torque. That's why we did not consider the torque due to F3, because there's none. That's why. So now, one is clockwise, the other is counterclockwise. So when you take the net, remember to put the signs. You know, clockwise is negative. So that's why we got 7.2 minus 5.7, which is 1.5 Newton per meter. And then I noticed that I'd made a calculation mistake. Goodness gracious. So I changed it to 4.08 Newton meter. I'm just as human as you are. Especially when you do it fast, you tend to make mistakes. But that's not an excuse. I know, but I'm just leaving it there without editing it to show you that if you're careless, anybody can make a mistake, even a professor. Just as human as you are. Okay? Here is another question from static equilibrium. Oh, this is overwriting. Let's see. Wow. So let's see where that goes. I gotta cut it out. All right. Here is the question. A 140 kilogram horizontal beam is supported at each end. A 320 kilogram piano rests a quarter of the way from one end. What is the vertical force on each of the supports? So you have a beam and you have a piano here, which is one quarter of the way. I've divided into 4 parts and try to put it like that. What is the vertical force on each of the supports? So we are asked to find this force, reaction force, and this one. All right, let's label the forces. So that's 140 times 9.8. That gives you the weight, and it's acting right through its center. This is F1, this is F2. And I had to think about it and say, hey, let me move the piano, make it smaller. So the weight of the piano is 320 times 9.8, which gives 3136 Newton. And remember the 2 conditions. First one, net force is 0. That means the total up force is equal to the total down. And that's how I put F1 plus F2, both being up, is equal to the sum of these two. And then I call this A and B because we got to specify where we're going to calculate the torque. So whenever you calculate the torque, you have to assume a point where you take as the pivot. In this case, I am calculating the torques about A. That means there will be no torque due to F1 because it's right at that point. And also that means that this and this both will create a clockwise torque, both trying to rotate it clockwise, while this reaction is trying to turn it counterclockwise. See that? And then all we got to do is multiply each force with the distance from A. So 3136 times 1 by 4. The real distance is not given. We don't need it. We just know it's a quarter of a way off. So 1 by 4 plus, when you multiply this, you're going to do half because that distance is half, right? This distance is half. And then that is the torque. And then you put it equal to the counterclockwise torque, which is F2 times 1. So that's 1 full length. That's why this was half and this was a quarter. And then make F2 the subject and calculate. And you would get F2. Once you get F2, just substitute the value of F2 into that equation and you get F1, and you get the reactions of the 2 supports. This is simply an application of the 2 conditions for static equilibrium. I hope you understood that. Right. Let's move on, and I'm just trying to explain this, Okay. Cut. Wow, here is a question that is again an application of static equilibrium. It looks tough, it's not that tough, okay? That's always the case in physics. So a uniform horizontal strut weighs 400 Newton. So that's this one. And it says uniform, that means its weight should be acting right through its center. One end of the strut is attached to a hinged support, you see that, at the wall, and the other end is attached to a sign, so you have the sign there, that weighs 200 Newton. The strut is also supported by a cable attached between the end of the strut and the wall. Assume that the entire weight of the sign is attached at the very end of the strut. Well, usually that wouldn't be the case, that would be somewhere here, but to make it easier for us to calculate, there is that approximation which wouldn't be so bad. So when I draw the free body diagram, I'm going to show the weight of the sign acting right here. And what do we have to find? We have to find the tension on the cable That is the tension here, and the force at the hinge of the strut. So how would the force be here? Would it be like along the wall? No. Would it be horizontal? No, it would be at an angle. Wow. So we got to find the force here, and we got to find the tension in the cable. Let's do it. So those are the forces that you see that I explained. That is 400 newtons. This is 200 newton. Tension and the force. Well, we know we got to resolve that force into its components. So that's depending on how you take the angle, you would get the x and the y components. Let me just, I'm erasing it, drawing again. Anyway, so here's the same diagram coming up there. I might as well show you the entire diagram. Here it is. So the force is resolved into Fx and Fy. Same thing with the tension. It's resolved into T cosine 30 and T sine 30. So you have the free body diagram here. And we're going to calculate what is the length of this. Okay, we just take it as 2. I just took it as 2 meter. Don't think it's given. Why do we take it as 2? Because we know that this then is going to be at the 1 meter mark. Right? That's all we need. You just need the ratio. So calculating the torque about this point, so that means we measure all distances from here, you get T sine 30, which is acting here actually, T sine 30 times 2, which is the counterclockwise torque, and then you have 2 clockwise torques. One of them would be 200 times 2, and the other one would be 400 times 1. Is there any torque due to this? Nothing, because it's acting right at that point. So that's why you see this. Counterclockwise torque is equal to the sum of the 2 clockwise. And from there I get the tension. See, tension is 800 Newton. And then you can calculate the force F in many ways, but what I did is, knowing that the vertical components must be equal, I set Fx as equal to T cosine 30, because I know they should cancel out. Why? The net force along any axis should be 0. So this must be equal to this. That's what I've done there, and I got F sub x. Same thing here. I know that Fy plus T sine 30, those are the 2 up forces, must be equal to the total down forces. See that? So I get Fy as 200 Newton. And if you have to find the magnitude of the force, then you use square root Fx squared plus Fy squared and find the force at the hinge. So now we have 2 more questions to go. Oscillations is an important chapter, and that has a lot of formulas. Study the general equation for simple harmonic motion for displacement, velocity, and acceleration. Do that. And also study the formulas for time period of oscillation of a loaded spring and a simple pendulum. And understand what resonance is, the energies involved in simple harmonic motion, what damped harmonic motion is, and what forced harmonic motion is. So look at all those. Here is an example where you have a 326 gram object attached to a spring and executes executes simple harmonic motion with a period of 0.250 seconds. If the total energy of the system is 5.83 joules, find A, the maximum speed of the object, B, the force constant of the spring, and C, the amplitude of the motion. So what are you given? You're given the mass of the object, 326 grams. You were given the time period and the total energy. And you're asked to find the maximum speed. So once you're given the total energy, you got to know the formula for total energy. The total energy of simple harmonic motion is what? 1/2 k a squared, where k can be substituted. Okay? We know that omega is 2 pi f or 2 pi by t. So using that, we can first find omega. You get omega as 25.12 radians per second. And since we know that omega is square root k by m, we can manipulate that and make k the subject to make it m times omega squared. And mass is 0.326 kilograms. And omega is 0.250 radians per second. And that's to be squared. And you find the value of k. Remember, k is spring constant, it's Newton per meter. Once you get k, use the formula for energy and make a the subject, because we're asked to find the maximum speed. So let's find the amplitude. A is the amplitude. So 2 times the energy is given as 5.83 divided by the mass. Divided by k. Divided by k. So once you do that, you get the amplitude as 23.9 meter. And we know that maximum velocity is at the mean position. When it's passing the mean position, right? Not at the, because at the amplitude, the speed is 0. And therefore, the formula for maximum velocity is simply a omega. That's why we needed to find a. So just multiply that. Again I've made some calculation errors. So that's 25.12 squared. That's what I had. That comes out to be 206 Newton per meter. 206 Newton per meter. So that changes the amplitude. So the amplitude is 0.238 meter. And so I'll have to redo that. That gives 5.98 meter per second. 5.98 meter per second. So actually I found the answers to A, B and C. B is the force constant, C is the amplitude, everything done. So now we come to the last question in this review. So here you're given a particle at an instant, 1 kilogram particle, its position vector is given, its velocity vector is given, and the force on it is given. And you got to find the angular momentum. So I wanted you to be aware that angular momentum is also in the exam. And what is angular momentum? Angular momentum is the cross product of R and P. R and P. R is the position vector, P is the linear momentum. And what is linear momentum? Mass times velocity. So angular momentum is the cross product of R with mass times velocity. You're going to see it. Angular momentum is a vector, of course. Any cross product gives you a vector. So that's R cross P. And since it's given in IJK notation, vector notation, we have to use matrices to calculate this. So first you have 2.0 I minus 4.0 J plus 6.0 K, which is R. And remember, in a cross product, the order of the vectors is important. So R first, cross P. And to find P, you got to have the mass, which is 1.0 kilogram, times the velocity, which is given in this format. Okay, the unit is meter per second for velocity, of course. So I've taken out the mass and I have ijk here, and then 2, -4, and 6. Oh, I hope I don't forget the -4, because it's -4. All right, so when you put the 2, -4, and 6, and then this one is -1 plus 4, 1. See that? And then I hope you know how to do this. To find the coefficient of I, you go -4 times 1 minus 6 times 4. That's what you have there. To find that of j, remember to put a negative before j, and then go 2 times 1 times 6 times -1. That's what you have there. To find that of k, so put plus k again. It's only negative for j there. And then you go 2 times 4 minus -4 times -1. So 2 times 4 is 8 minus -4 times -1 is +4. So you get -4. You see that? Be careful. And then you get this as the angular momentum of the particle about the origin. And in that question, I have only calculated the angular momentum. I did not calculate the torque. But you know that you can calculate the torque using what? What is the formula? It's the cross product of R and F. Oh, I think I've done it on top. My goodness, I didn't see it. Oh, so here is the torque. ijk again. You have R, the coefficients of R, and the coefficients of F. See that? 10, 15, and nothing for K. That's why it's 0. And by the same process, you get this as the value for torque. And then the C part says, what is the time rate of change of the particle's angular momentum at this instant? What is that? Time rate of change of the angular momentum. So that is dl by dt. What is dl by dt? It is the torque. These are the questions on the review. So make sure you study this and do well on the exam. Thank you.